Hi everyone, and welcome to the dApps on Nervos CKB workshop. My name is Jordan, and I'll be narrating today's presentation, which was originally created by Shuiji. This is a multi-part workshop and will cover the entire process of developing a modern dApp, including all on-chain and off-chain components required to build on Nervos CKB. This workshop is divided into 3 parts. The first is an introduction to the basic concepts, including some commonly used design patterns. The second demonstrates our Capsule framework, a tool created specifically for writing on-chain smart contracts in Rust. The third is Lumos, a complete dApp framework for interacting with the blockchain using JavaScript or TypeScript. Today's presentation contains 3 parts. First, I will provide a basic introduction to Nervos CKB. Next, I'll describe the programming model used, and finally, I'll demonstrate some of the common design patterns. I'll also be talking about some of the fundamental differences that make programming on Nervos unique, including the benefits and challenges associated. First, let's look at what Nervos CKB is. CKB stands for Common Knowledge Base. It represents Layer 1, the lowest level blockchain that supports the rest of the Nervos ecosystem. We believe that a layered approach to blockchains will deliver the best overall solution, similar to how the network stack of the internet itself is multi-layered. The concerns of Layer 1 are security, will my assets remain safe, and flexibility, will it adapt to the unexpected requirements for decades to come. Layer 2 solutions will vary based on the requirements of the application. For example, some may require low latency, others may require high TPS. These are application-specific use cases, and there isn't a single approach that fits them all. Layer 1, on the other hand, must provide a foundation for the entire ecosystem, including all the different types of layers above it. Layer 1's concerns must support that goal. By focusing exclusively on security and flexibility, we are providing a system that will service the future needs for decades to come. The core design of Nervos CKB is inspired by Bitcoin's programming model. Blocks are created in a connected chain forming what we call blockchain. Each block contains one or more transactions. A transaction is how Bitcoin describes a change in state. This state change occurs when existing inputs are destroyed and new outputs are created. Any input which has not been used is known as an unspent transaction output, or a UTXO for short. Each one of these UTXOs can only be used one time as an input, which is how Bitcoin enforces the rules that prevent double spending. It is all of these existing UTXOs combined that represent the current total state of the blockchain. Each UTXO has 2 parts. The first is called value. It contains the amount of Bitcoin contained in the UTXO. The second is the script. This is the code that is run on every input when the transaction is executed. It is only after all scripts on all inputs are executed successfully that the transaction will be considered valid and it will be recorded on the blockchain. I'll describe what's going on here from another angle. Bitcoin is implemented based on a public-private key signature system. You first generate a private key which is used to unlock your wallet. But how is this reflected on chain? This is done by using the private key to demonstrate proof of ownership of a public key that is tied directly to the UTXOs. In order for a transaction to process successfully, they must adhere to a specific protocol that provides the required signatures in a structure called the witness. This protocol provides all of the information necessary to match a signature from the witness to an executing script within a UTXO from the transaction's inputs. And it does this in a way that forbids any type of change to be made to anything in the transaction without requiring new signatures to be created. This allows the holder of the private key to prove they are authorizing specific UTXOs to be used in a specific transaction. It is only after authorization has been proven by the holder of the private keys that the Bitcoin in the UTXO can be spent. Ethereum uses an account-based model, which is very different from Bitcoin's UTXO model. Ethereum is also a chain of blocks filled with transactions, but each transaction includes arguments and a smart contract. There are no UTXOs, and instead Ethereum has a single global world state. The smart contract state is a segment of the world state, and it consists of a balance in ETH and a key value store. When a smart contract executes, it reads the old state, then updates the values as needed to create a new state. In the current structure, we have 2 entries in the key value store. The key of the first entry is A, and the value is 1. The key of the second entry is B, and the value is 9. What this transaction does is it modifies the key value store, changing the value of B from 9 to 7. It is the rules of the smart contract that dictate the changes made to the state. This is fundamentally different from the Bitcoin model we saw before. In the Bitcoin model, the transaction describes all the data that will be represented on the chain. The inputs represent the current state, and the outputs represent the new state. In Ethereum, only the smart contract can modify the state. In Bitcoin, the contract cannot modify the state at all. In the Ethereum model, the transaction describes the action to be taken, and then the smart contract modifies the state. All the work to generate the output data is done on-chain by the smart contract. The goal of both the Bitcoin UTXO model and the Ethereum account model are the same, to modify the state, but their approaches to doing so are fundamentally different. Nervos CKB uses the cell model, which is based on Bitcoin's UTXO model. Cells are a similar concept to UTXOs, but with a new structure that enables more flexible functionality. A UTXO has a single value and a script. This value is the amount of Bitcoin, and the script is used to ensure that only the proper owner can spend it. A cell expands this into 4 fields. The first is capacity. This represents how many CK bytes are held within the cell. The second is data. This allows any type of arbitrary data to be stored on-chain. This could be any data that's used by the smart contracts, or even smart contract code itself. In the second presentation, we will demonstrate how to write a smart contract, and there we'll show you how it closely relates to the structure of a cell. The third is the lock script. This is a script that's similar to Bitcoin script, and it ensures that the cell can only be used by the proper owner. And the fourth is the type script. This provides advanced smart contract functionality, allowing the creation of programmable assets like tokens. When we look at a CKB transaction, you should notice a strong similarity to a Bitcoin transaction. Along the left side, we have input cells. These cells represent the current state and are destroyed in a process called consumption. Just like with Bitcoin UTXOs, a cell can be used only once. On the right side, we have output cells. These cells represent the new state, and they will be created once the transaction is confirmed on-chain. When a transaction is executed, the lock scripts and type scripts will be executed in a specific order, and the transaction is not considered valid unless all scripts exit without error. First, the lock scripts execute on all input cells. Each lock script verifies that the proper authorization was provided to allow the cell to be used as an input. Next, the type scripts execute on all input cells and all output cells. The type script enforces smart contract-like functionality and ensures that the developer rules are followed for any state changes. Because a transaction contains both input cells and output cells, the future state is deterministic and can be predicted with absolute certainty. In summary, each transaction contains a deterministic result state. What is submitted in the transaction is guaranteed to remain unchanged after it's confirmed on the chain. On-chain scripts only validate state changes. This means that they do not generate the data in the transaction. Instead, they only ensure that the transaction conforms to the rules set forth by the developer. Next, we'll talk about CKB-VM. CKB-VM is the virtual machine used to execute on-chain smart contracts in Nervos CKB, and is based on the RISC-V instruction set. RISC-V was created to power the next generation of hardware processors. The target users are hardware manufacturers that design CPUs. RISC-V was designed for hardware, not blockchain. However, after research, it was determined that the design of RISC-V is ideal for usage in blockchains. When a CPU has been released, no more changes can be made. The instruction set is fixed, and that instruction set might be used for decades. This feature makes it very suitable for blockchains, because data on the blockchain cannot be changed after it's created, just like hardware cannot be changed after it's released. In the blockchain field, any form of a fork is a major operation that should be done only if absolutely necessary. Since the RISC-V instruction set is stable and set in stone, this greatly reduces the likelihood that a fork will be required in the future. Since RISC-V is an instruction set designed for a processor, it both satisfies the need to maintain stability and remain powerful. Anything that can be done on a processor can also be done on CKB-VM. Here's a real code example. On the left is the simplest code in the C programming language for calculating a Fibonacci sequence. On the right are the RISC-V instructions generated when the code is compiled through GCC or LLVM. On Nervos, the CKB-VM executes these instructions completely unmodified, exactly as they are generated. Today, most hardware manufacturers have support for RISC-V. Both GCC and LLVM can target RISC-V hardware, and many commonly used languages such as Rust, Go, C, and C++ can all compile directly to RISC-V. Another advantage of RISC-V is that it's very streamlined. 2 pages is enough to describe all of the instructions, including the RISC-V standard instruction set. CKB-VM only used the parts of the standard shown in the figure. These 103 instructions of RISC-V are enough to facilitate all the needs of CKB-VM. CKB-VM delivers the power of a real computer embedded in a blockchain. In fact, you can take a compiled smart contract and execute it on a RISC-V Linux computer completely unmodified. This flexibility allows CKB-VM to support all existing use cases such as tokens and atomic swaps. Because CKB-VM is so close to hardware, it can also meet some new requirements. A user can implement any cryptographic primitive necessary simply by inserting a new library into their existing codebase. There is no need to hard fork to customize encryption algorithms used by smart contracts. In fact, there are no hard-coded encryption algorithms on Nervos CKB. All encryption algorithms are provided through on-chain smart contracts directly. CKB-VM is flexible and powerful enough to run another virtual machine inside of CKB-VM. For example, WebAssembly is a common virtual machine for some other blockchains. We have tools that can compile WebAssembly programs into RISC-V programs directly. This means that smart contracts written for WebAssembly on other blockchains can run seamlessly on top of Nervos CKB. Another example is Polyjuice, an Ethereum-compatible layer for Nervos CKB that's currently being worked on. It allows code designed for the Ethereum virtual machine to be compiled to RISC-V. This means that code written in Ethereum's Solidity smart contract language can be run on CKB-VM directly. Using the same method, we can also support other platforms such as Libra and EOS. The key takeaway is that CKB-VM will allow the support of a continuously growing number of use cases in the future. This will give Nervos CKB a level of flexibility that is unmatched in the industry. Here's a basic transfer scenario. In Ethereum, all state information on the current chain is contained in the world state. In the old world state, Alice has 500 ETH, Charlie has 500 ETH, and Bob has none. If Alice wants to transfer 210 ETH to Bob, Alice needs to generate a transaction which will modify the world state. Alice generates a transaction that contains an action saying, transfer 210 ETH to Bob. After the transaction is executed, Alice has 290 ETH and Bob has 210 ETH. The ETH balances are updated and available as part of the world state. On Nervos CKB, the state of the chain is obtained by calculating all the individual cells together. In this example, Alice has 500 CKB, Charlie has 500 CKB, and Bob has none. Notice that Alice's balance is contained in 2 cells, one for 200 CKB and one for 300 CKB. Charlie has 1 cell with 500 CKB. Alice wants to transfer 210 CKB to Bob and must create a transaction to do so. The input cell in this transaction is Alice's cell containing 300 CKB. After the transaction is executed, the cell containing 300 CKB will be consumed and 2 cells will be generated in its place. One output cell belongs to Bob. It contains 210 CKB that was sent from Alice. The other cell belongs to Alice and it contains the remaining 90 CKB. After the transaction is executed, Alice has 290 CKB. This amount is determined by adding up all of the balances of all the cells owned by Alice, which is 1 for 200 CKB and 1 for 90 CKB. Bob has 210 CKB contained within a single cell. Charlie's balance is unchanged at 500 CKB within a single cell. But what determines if a cell belongs to Alice or Bob? The answer is the lock script, which we mentioned earlier. In a Bitcoin UTXO, the value field stores the amount of BTC, and the script contains the public key of the owner. Nervos' cell model is similar. The capacity stores the amount of CKB in the cell, and the lock script will include a public key of the owner. Alice's cell will contain Alice's public key. Bob's cell will contain Bob's public key. The lock script determines who the owner of the cell is. On Nervos, an account is represented as a collection of cells. All of the cells which have a lock script containing Alice's public key belong to Alice. All of these cells owned by Alice combined together constitute Alice's account. Similarly, a collection of all of the cells with lock scripts containing Charlie's public key constitute Charlie's account, and a collection of all the cells with lock scripts containing Bob's public key constitute Bob's account. The concept of an account is often mentioned in Ethereum, EOS, and Libra. It's a relatively familiar concept and very similar to a traditional bank account. But Nervos CKB is different. An account in CKB is a collection of cells owned by a user, and ownership is determined by the lock script. Next, we'll look at an Ethereum ERC20 token transfer. In Ethereum, every unique ERC20 token has a contract state, which is in turn part of the world state. This contract state tracks individual balances. Here we see the contract state of the BAT token. Alice has 100 BAT tokens, Bob has 200 BAT tokens, and Charlie has 50 BAT tokens. Alice creates a transaction and transfers 10 BAT to Bob. After this transaction confirms, Alice has 90 BAT tokens and Bob has 210 BAT tokens. In the Ethereum model, all individual balances are tracked within a single smart contract. The smart contract of the BAT token contains the balances for Alice, Bob, Charlie, and anyone else who has BAT tokens. If we looked at a different token, like the USDT token, it would similarly contain individual balances for every user. In short, every ERC20 token has a smart contract that contains a collection of all individual balances within its contract state. Ethereum's smart contract state provides a central point for storing account balances. In Nervos CKB, there is no similar concept. The current state on Nervos CKB is a collection of all unspent cells on the current chain. Of course, we could implement a mapping system that unifies the state, containing the balances of all tokens in a single cell, but this is artificially creating a central point of storage. Is there a way to split the logic so that each user can own their own cell and use it to save a particular token? For example, Alice has 3 cells. Each contains 1,000, 600, and 1,200 tokens respectively. Bob has 2 cells containing 800 and 1,800 tokens respectively. Can this result be achieved? The answer is yes, it is possible. We designed a structure in Nervos CKB called Simple UDT. This is similar to an ERC20 but with some simplifications and improvements. The structure of a simple UDT cell is as follows. The capacity saves the amount of CKB the cell currently has. The data contains a 128-bit integer which represents the amount of tokens the cell contains. The lock script defines the owner of the cell and will contain the public key of the respective owner. The TypeScript defines the smart contract rules that control how the state of the cell can change. This cell is using a simple UDT TypeScript, which means it must follow the smart contract rules that define how a simple UDT works. Every different kind of simple UDT token will use the same TypeScript but with a different unique identifier. This is similar to the object-oriented programming concepts of object classes and object instances. The TypeScript is similar to an object class. It defines the common behaviors of all object instances. A cell using this TypeScript is similar to an object instance. It has the behaviors defined in the object class, but it contains its own state. In the next workshop, we'll dive into how a TypeScript works, but for now we'll keep it simple. A cell's TypeScript field contains the simple UDT smart contract, and this makes the cell a simple UDT cell. The TypeScript will ensure that users can only use this cell as intended by the smart contract developers. For example, the owner of the simple UDT is free to transfer their tokens to other users without restrictions. However, the user cannot mint themselves a bunch of new simple UDT tokens out of nothing. The TypeScript ensures that these developer-defined rules are always enforced. Let's take a look at how a simple UDT transfer would occur. In this example, all cells have a simple UDT TypeScript and a UDT identifier for token A. Alice starts with 2 cells. One has 600 tokens and the other has 1,000 tokens. Bob starts with 1 cell with 800 tokens. Alice wants to send 100 tokens to Bob and creates a transaction. The input to this transaction is Alice's cell with 1,000 tokens. In the outputs of this transaction there are 2 cells. The first cell has 900 tokens and Alice is the owner. The second cell has 100 tokens and Bob is the owner. The simple UDT TypeScript on the cells within the transaction will ensure that all of the values are valid. If we take the sum of the tokens in the inputs and outputs, they are equal. The inputs have 1,000 tokens. The outputs have 900 and 100 tokens, which add up to 1,000. This transaction is valid and would be allowed to confirm. The result after the transaction confirms would be Alice having two cells, one with 600 tokens and the other with 900 tokens. Bob would also have two cells, one with 800 tokens and the other with 100 tokens. Now let's change the value of Bob's output to 150 tokens. The inputs still have 1,000 tokens. The outputs have 900 and 150 tokens, which adds up to a total of 1,050 tokens. This transaction is invalid because the rules of the simple UDT typescript forbid tokens to be created out of nothing. If submitted to the network, this transaction would never confirm. There's an additional concept about the cell model that we didn't discuss earlier. You already know that the capacity field indicates the amount of CKB in the cell, but there's a specific reason why it's called capacity. The capacity of a cell is the total number of bytes that a cell can occupy on Nervos CKB. When talking about Nervos' native token, CKB is short for CK byte. Owning one CK byte allows the owner to store 1 byte of data on Nervos CKB. In order for the cell to be valid, it must have equal or more capacity to hold all of the data in all fields. Let's take a look at the data requirements for a simple UDT cell. There are 4 different fields. Capacity uses 8 bytes of data because it's a 64-bit unsigned integer. Data uses 16 bytes because a simple UDT uses a 128-bit unsigned integer. The lock script uses 53 bytes and the typescript uses 65 bytes. If we add all of this up, we get 142 bytes for the cell's required storage. Therefore, at least 142 CKB must be added to the cell's capacity or the cell cannot be created. Let's go back to the previous scenario. Alice transferred 100 tokens to Bob, but doing so required an additional cell. Alice would need to provide enough CKB to satisfy the storage requirements of this new cell. Since this is a simple UDT cell, it will occupy 142 bytes. To create a cell for someone else, you must also give them the required CKB with the cell that you create for them. When Alice transfers 100 tokens to Bob, it is also implying the transfer of 142 CKB to Bob. Therefore, transferring simple UDT tokens is also transferring CKB. If you're transferring a large number of tokens with significant value, then the CKB requirements may be negligible. But what if Alice only wanted to transfer a single token to Bob? Requiring an additional 142 CKB would be unreasonable. Fortunately, there's a solution for this problem. In this transaction, Alice is once again sending 100 tokens to Bob, but this time Bob is providing his own storage space. If one of Bob's existing simple UDT cells is used as an input, then no additional cells are created in the output. The capacity from Bob's input cell will carry over to his output cell. This way, Alice does not have to provide an additional 142 CKB to create a new cell for Bob. Alice's input cell has 1,000 tokens and Alice's output cell has 900 tokens. Bob's input cell has 800 tokens and his output cell has 900 tokens. A total of 100 tokens have been transferred from Alice to Bob without any additional CKB requirements. However, there is one new problem. Alice cannot create this transaction alone. In order to use Bob's cell as an input, Bob needs to provide his signature. This would require both Alice and Bob to be online at the same time to mutually sign this transaction. This is too inconvenient to be practical, but fortunately, there is a way to work around it. What if a cell can be unlocked automatically when someone deposits to the cell? The concern would be that once the cell is unlocked, someone could steal anything inside of it. For example, a cell contains 200 CKB. If someone tried to steal those CKB, then we need the cell to remain locked. If someone wants to send CKB to the cell, then we need the cell to unlock for this purpose. The same policy would apply to tokens. The cell should remain locked unless someone is sending tokens to the cell. This functionality can be achieved using a special lock script called the AnyOneCanPay lock, which is sometimes abbreviated as ACP. Bob would replace the default lock script on his simple UDT cell with the AnyOneCanPay lock script. This special lock script allows Bob to use his cell exactly as he normally would, but it adds one new feature. When Bob's cell is included in any transaction, it will analyze the structure of the cells included. Specifically, it looks at the capacity and token value of Bob's input cell and ensures that Bob's output cell has equal or more capacity and tokens. This indicates that someone is depositing to the cell, in which case it will automatically unlock. Using the default lock script would have required Bob to sign the transaction, but using the anyone can pay lock removes this requirement. In this example, Alice is sending 100 tokens to Bob. Alice is creating the transaction and signs it to allow her input cell to unlock. Alice includes Bob's anyone can pay cell as an input, but neither Alice or Bob signs to unlock Bob's cell. When the transaction is submitted, the anyone can pay lock script executes and sees that the token balance is increasing, indicating a deposit and unlocking automatically. This transaction is valid and will confirm as expected. The anyone can pay lock script is an excellent example of the flexibility of CKB VM. This functionality was achieved without any kind of special provisions in the Nervos CKB protocol. The anyone can pay lock script is a normal script and can be created by any developer. Using timestamps within smart contracts is a common way of facilitating time-based conditional logic. Time services are a very important piece of blockchain infrastructure and have all kinds of uses from gaming to lending and DeFi. In Ethereum, time is easily provided through their model. In Nervos CKB, it's a little less straightforward. This is because transactions are deterministic. The outputs contain the resulting state, and this is generated before the submission to the network. Since we can't guarantee that a transaction will be included in a particular block, it's not possible to have accurate time. However, there are two methods to utilize time on Nervos CKB. The first method uses a special field on the inputs called since. There's also a counterpart value called previous output, but we'll just focus on since for now. Since is used to control when a transaction can be committed on-chain. For example, if the since value is set to tomorrow, then it will not be possible to commit the transaction on-chain until tomorrow. Since supports 3 different time formats: timestamps, epochs, and block numbers. Smart contracts have the ability to read the since value from the inputs. This yields an approximate baseline time value that can be used by the smart contract. For example, if the since value was 9 a.m. in the morning, then the smart contract would know that the current time must be on or after 9 a.m. In actuality, it could be 10 or 11 a.m. or much later. So it doesn't provide an exact time value, but it does provide a lower bound to work with. The second method uses a special structure called header depths. This gives developers a way to provide block header data from any committed block to the smart contract. The block header contains block numbers, epochs, timestamps, and can be from any committed block in the history of the blockchain. The smart contract can read these values to get a lower bound time value. For example, if the current time is 10:10 a.m. and you provide a header depth from a block that was committed at 10:05 a.m., then the smart contract will know that the time is at least 10:05 a.m. If the current time is 10:10 a.m. and you provide a block that was committed at 4 a.m., then the smart contract will know that the time is at least 4 a.m. Absolutely accurate time is not possible, but in actual use, this is good enough for most cases. Even in Bitcoin and Ethereum, time values are relative. They are guaranteed to be sequential, but not guaranteed to be accurate. For an example of a practical implementation, we recommend reviewing the Nervos DAO source code. It uses both header depths and since values, and it is an excellent example of how to use these two structures effectively. Next, we'll introduce the concept of open transactions. We'll start by expanding on the previous simple UDT example. Alice wants to send 300 of token A to Bob, and in return Alice would like 250 of token B. Let's go through the inputs and outputs from top to bottom. In row 1, Alice has an input of 1000 of token A and an output of 700 of token A, a decrease of 300 tokens. In row 2, Alice goes from 800 to 1050 of token B, an increase of 250 tokens. In row 3, Bob goes from 600 to 900 of token A, an increase of 300 tokens. And in row 4, Bob goes from 400 to 150 of token B, a decrease of 250 tokens. To generate this transaction, Alice and Bob will need to communicate off-chain. This will take a series of back-and-forth interactions, and once a transaction is formed, both Alice and Bob will need to provide their signatures. Let's split the transaction in half into 2 separate concerns. Alice's concern is that she receives 250 of token B while giving 300 of token A. Bob's concern is that he receives 300 of token A while giving 250 of token B. On Nervos CKB, it is possible to have each party sign only the portion of the transaction that they are concerned with. This is where open transactions come into play. If Alice and Bob want to complete this transaction, then Alice only needs to sign the parts of the transaction that she's concerned with. Bob only needs to sign the parts of the transaction that he is concerned with. These two parts are technically independent transactions, but if submitted to the network independently, they would be invalid. Therefore, we refer to these as open transactions. Each open transaction is invalid if submitted independently because they both have requirements that are not fulfilled. In this example specifically, Alice's open transaction has an increase of 250 of token B, and Bob's open transaction has an increase of 300 of token A. As we know from the previous examples, you cannot create tokens from nothing, so if they are submitted independently, these transactions are invalid. Once these two open transactions are combined into a single transaction, then all of the concerns are fulfilled and the entire transaction can be committed to chain. The open transaction structure can also be used to facilitate a decentralized exchange. Alice and Bob can submit their open transactions to a matching service pool. Their open transactions will remain in the pool with those from other third parties until a match is found. When a successful match is found, the matching open transactions will be collected and added to a single transaction that is submitted to the network. This process is completely non-custodial. Alice and Bob's open transactions are signed in such a way that either party will get the result they expected or the transaction will not confirm. Now let's talk about storing data on-chain. First and foremost, storing data on-chain should be minimized because it increases costs, but when the need arises, it is possible. In Ethereum, data is stored in the KV store, which is short for Key Value Store. This allows multiple named values to be managed independently. In this example, there are 3 different key value pairs in the KV store, and this data is stored in the Ethereum smart contract state. On Nervos CKB, you can achieve the same result by saving the data in a cell's data field. This data field stores raw untyped data of any form. This means it's up to the developer to define any formatting or typing of the data. In this example, we are defining both the key and the value as 256-bit unsigned integers. This means that any key or value will consistently occupy 32 bytes or 64 bytes for a pair. Assuming we have 3 pairs, that's 192 bytes of data. The data could then be saved by writing the key and the value pairs in order to the data field. 1111, 2222, ABCD, 1234, dead beef, 42. Remember, in this example, all values are 32 bytes even if they seem smaller. As long as these values are read and written in a consistent format, the smart contract should have no problem accessing the data easily. This is a simple design that may work for many scenarios, but it becomes problematic for large amounts of data. Each time any value is changed, the entire cell's data area must be rebuilt. This is because of the deterministic nature of transactions. All values, changed or not, must be presented within a transaction's outputs. If you only have 3 data pairs, it's not a problem, but if you had hundreds or even thousands, it becomes a much more significant issue and a waste of resources. Fortunately, we can work around the aforementioned issue using an alphabetical key value store. TiKV is a good example of how this can be implemented. The problem that TiKV solves is when a dataset is so large that a single machine cannot save all the data, so it's distributed to 2 or more machines. The data is split up using lexicographic ordering to determine which region a key value pair will reside. Keys A to B would reside in region 1. Keys B to C would reside in region 2. Keys C to D would reside in region 3. Different key ranges will be split up and mapped into different regions. We can do the same in Nervos CKB. Here's a simplified example of how we could map our previous data set. Key ranges from 0000 to A000 would be in the first cell. Every key after A000 will be placed in the second cell. This splits up the data between the 2 cells deterministically based on the key. If we add another pair with the key 3333, it will map to the first cell automatically. This is a simple example with 2 cells, but a real implementation could have as many cells as is necessary. State is represented as a collection of cells, so a large state would need many cells. This example shows just one way of splitting up the data. There are many other possible ways, and an optimal solution will vary depending on the requirements. More on-chain data means more capacity requirements, so it's important to keep in mind the cost of storage when designing any on-chain data solution. A structure known as a sparse Merkle tree can help to reduce the amount of on-chain data. In our previous examples, the key was expressed as a 256-bit integer. We can easily use this value to create a sparse Merkle tree. Each different bit is a different branch. This means that a 256-bit integer yields a total of 2 to the 256th power possible leaf nodes. In this example, the green nodes are empty, meaning there is no value at that position. This is why it's called sparse, because all keys are not required to exist at any given time. Once our data is in this tree, it is hashed at each level until a single root hash is produced. This root hash is cryptographically guaranteed to represent only this exact tree structure. Even if a single bit was changed anywhere in the tree, the root hash would be completely different. We can take the root hash of the sparse Merkle tree and store it on-chain. In this example, the root hash is stored in the cell's data area. As the root hash changes, it is continuously updated within the cell. The actions associated with each change are placed into the witness. This allows us to prove the state of a very large data structure with absolute certainty while only storing a single 256-bit root hash in the on-chain state. The result is that a transaction chain is created of all the operations required to rebuild the tree. By starting at the beginning of the tree and replaying the actions from every transaction in order, the tree will be rebuilt exactly. The root hash, which is stored on-chain in every transaction, ensures that the full history of the tree is recorded accurately and that it is unaltered at every step. We have a library which uses this pattern called the CKB Simple Account Layer. It provides an abstraction to use an Ethereum-like account model on Nervos CKB, including the key value store functionality. Just as we described earlier, only the root hash of the sparse Merkle tree is stored on-chain, which gives a huge cost savings while retaining absolute provability guarantees. Back to the subject of on-chain data. Blockchains incur significant latency and expense to store or change data, which makes them unsuitable as a primary data store for real-time applications. However, we do not view this as a shortcoming because the purpose of a blockchain is to gain global consensus. Achieving widespread global consensus is inherently expensive, and it cannot be done with large amounts of data, but it is very valuable when used correctly. In order to take advantage of it, you must be willing to pay the price. This is why we minimize the amount of data that goes on-chain. The sparse Merkle tree pattern only stores the root hash, which makes it much more effective for on-chain use. Only the root hash is part of global consensus, but this single hash will guarantee all of the data within the tree. This is the essence of Nervos CKB. Only the most important data, which we refer to as common knowledge, is kept on-chain. This allows for the highest level of global decentralization while delivering the strongest guarantees to a much larger body of information that is stored off-chain. In summary of today's workshop, first we learned that each transaction contains a deterministic result state. The final state is contained in the outputs and is generated before being submitted to the network. You will never be surprised by the end result when interacting with the smart contract. Second, on Nervos CKB, the on-chain smart contracts only validate state changes. Generation of new states is done off-chain. The purpose of a smart contract is to ensure that transactions conform to the rules set forth by the developer. Third, CKB-VM enables a very high level of flexibility. This allows developers to freely implement multiple different models and design patterns. Lastly, only the most essential data, known as common knowledge, should be kept on-chain. As shown in the sparse Merkle tree example, complete data guarantees are still possible while only keeping a small amount of data on the chain. As a final topic, I want to emphasize the meaning behind CKB, which is short for Common Knowledge Base. CKB is the foundation for global consensus within the Nervos ecosystem. In order to have a strong foundation, decentralization must be maximized. This is why only data of the most critical importance should be stored on-chain. This allows us to have the benefits of global decentralization while avoiding the disadvantages of blockchain performance. We believe that this is the best way to utilize blockchain technology, and it is the core principle behind the design of the Nervos ecosystem. If you have any more development questions, we recommend that you join us in the Nervos Discord server. There you'll find the DevChat chat room, along with a number of other chat rooms dedicated to various development topics. If you prefer Telegram, you can also find us on the Nervos Network CKB Dev chat room. My name's Jordan. You can find me on Discord, Telegram, and Twitter. Feel free to reach out to me directly if you have any questions about this presentation or about Nervos in general. Thanks for watching.